Now that we know how to build a regression model, in this session I would be focusing more on whatever the outcome that the regression model has given. How do I talk about the important predictors? Which one of them are important and which one of them are unimportant? So what we will try to do is, okay, let's say I have a data set here which has the price, square feet, bedrooms, bathrooms, offer. Let's say I'll consider these four, right? Probably I could even consider the brick and neighborhood also, but for time being I'll not consider them. I'll try to include them for another analysis at a later point. Initially what I want to do is using these four as the independent variables, right? I'll use these four as the independent variables and I'll try to predict the price. Okay, so we'll run our regression model again, wherein I'll take this as the dependent variable and these four are looked at as the independent variables and the regression model is run. Wow, something is coming out in terms of R squared, right? The R squared has come out close to 69.8 or 70%. Now if you see, this is what is the interesting part. Even the adjusted R squared is 68.83%. It's an indication that the price of the house is not exclusively based on square feet. There is a possibility that it is very much based on the number of bedrooms that are there, number of bathrooms that are there, and probably the number of offers that it is receiving for a purchase and a sale. Now, which means these four taken together, they are able to contribute to almost 70% in the variability of the price of that particular price of the apartment. Now what we are trying to say here is the remaining 30% might not be contributed by these four variables, which means there could be some other variables. Probably we did not take that brick and we did not take into consideration the direction. So there could be many more variables which we might not have considered or which could play an important role in the pricing of the apartment, which we might not have considered. Or I might very well conclude that 30% is the randomness that is there in the price of the apartment, which cannot be predicted with a model, right? So at least one thing here, the R squared and the adjusted R squared are much higher, which means compared to using a one variable, only the square feet, or using square feet and the bed together, it's better that I use all these four so that I can come out with a much better prediction model. Now, what is this equation that has come out here? This equation is telling me that it is minus 17,347. The price is coming out like this. The price is coming out as minus 17,347 plus 61.83 times the SFT plus 9,319 times the number of bedrooms plus 12,646 times the number of bathrooms minus 13,601 times the number of offers. The more and more offers come, it is going to decrease the price, and for each additional square feet is going to increase the price of the apartment by $61. Each additional bedroom is going to increase the price by 9,319, whereas each bathroom is going to increase the price by 12,646. Right? Now, okay, this is an equation, fair enough. Now, based on whatever the coefficients that have come, I want to know which ones are really significant and which ones are really insignificant here, right? I really want to know which of the variables are significant and which of them are insignificant. And that is what is analyzed through the signal to noise ratio. Here, signal is nothing but the value that comes as a coefficient, and along with it, the tool is computing the standard error around the predicted value, a standard error around a predicted. So the magnitude wise, the signal, I am looking at the magnitude of the signal relative to the noise. This is the noise part, this is the signal part. So signal is the coefficient estimate that came out. Noise is actually the standard error which talks about the variation around the slope. The variation around the slope. So here, now that I can use any number of predictors in a regression model, I want to know which of them are important, which of them can be ignored, which of them can be omitted, right? So that is where I don't end up adding some kind of dummy variable, some kind of nonsense variables to my model, which may not create any kind of impact on my final prediction. So I have to really identify, are all these significant, or probably is there anything which is insignificant and directly can be ignored. Now this is where we work on signal to noise ratio, as the word itself is saying. I'll try to compute the signal value and divide it by the noise value. So signal to noise in all these cases. Now which means the signal value is 7.4 times that of the noise. Here it is 4.3 times that of the noise, 4.0 times that of the noise, and 10 times that of the noise, whereas here it's just 1 time that of the noise, 1.36 times that of the noise. I'll ignore the sign here. Now, what is more important for me is, the more and more the stronger the signal is in comparison to its noise, the variable is more and more significant. So probably this variable is very significant because this value is 10 times to that of the noise. Probably then this is the variable which is more significant. These two are also significant to some extent, whereas this one is one of the least significant in the lot. Now this is one way. Probably if you look at the computation, this T-stat column is actually representing the same element, wherein I am dividing the signal value by its corresponding noise value, and that is what is working out as a part of the T-stat, right? Either I can do it manually, or when I am using the tool, the T-stat is directly giving me the same signal to noise ratio. Now, okay, here it is 1, here it is 7, here it is 4. Now what, do I have any kind of a cutoff? Do I have some, when do I say the signal to noise ratio is significant? What is that number where I take a call that this is significant versus this particular variable is significant? Probably if I get, instead of 4.33, if I have got 1.33, do I take it as significant? Do I take it as insignificant? What if it is 2.33? Now I need to have a clear understanding of which of these variables are significant and which ones are not. Now, I want a cutoff value, right? Which signal to noise ratio results in important relationship and which of them results in an unimportant relationship. And that is where we are bringing the concept of p-value. Here the p-value is already computed by any tool and is presented to us, but we need to interpret that value to make a decision. Now, the p-value is nothing but it's a probability value that the probability that whatever the predictor that you are choosing has no relationship with the response. Now it says here, this is the probability, there is a 17% chance that the intercept is not related to the response. Or probably the other way of looking at this is a very small value. E minus 11 is 1.2 into 10 to the power of minus 11, which is nothing but 0.0000, 10 zeros are there and 1 2. That is the probability that square feet has no relationship with the price, which means there is a large possibility that square feet is related to the price. Here also it is like 0.000297 chance that bedrooms has no influence on the price. Similarly 0.0000845 that bathroom has no influence on the price. Now here what we could see is the p-value whatever is coming out, it is the probability that the predictor variable which we are using has no relationship with the response, which means the lower the p-value, higher will be the statistical importance of the predictor, and higher the p-value, lower is the importance, which means wherever I am getting a very low value, and typically the cutoff is 0.05, right? Generally we look at 0.05. If the p-value is less than 0.05, I'll say that all these variables, each of the variables are significant, they are contributing to the price, but any of the p-value greater than 0.05, I'll directly conclude that that particular variable is insignificant and it does not contribute to the price, right? So the lower is the p-value, higher is the importance of this predictor. And a typical way of talking about the p-value is it's the probability that the observed signal, whatever the observed value that we have got, is just because of a random chance, right? It's not a significant number, it's just some random number that has come. That is an indicator of the p. So I am always looking at a very lower value of p, typically less than 0.05, just to make a conclusion that whatever the signal that I am observing is really real and it's not just a random chance, right? So if at all, in this case at least I don't get any except for this, which generally we don't remove, except for the intercept because it's not a variable. Except for this, I don't see any other variable which is insignificant here. All the p-values are less than 0.05 only, so I don't need to ignore any of them. But in case in any model, if I see that one or two or three variables are insignificant, then it's always better that I remove them, right? Once I remove them, I can get a much better model out of that. So statistically insignificant variables should be removed, and after that the model needs to be rerun to get a better picture of the relationships. But now, okay, I'm done with the statistical model. Here my model is predicting the price. The goodness of fit of the model is around 70% in the R squared. Each of the four variables are contributing to the price. But now the real problem comes. Okay, statistically my model is done. But how much practical it is. So this is where two statements come in very handy. The predictor, whatever I have included here, in some cases what might very well happen is the weight of the owner also might give a p-value less than 0.05. So we have to be very clear there. Just because the predictor is statistically important, I should not say that it is practically useful. So which means the way I have to go with is, first try to brainstorm whichever the values might be practically useful for predicting the price. and then look at the statistical importance of those variables through a regression. It's not the other way. It's not that first you take the data and based on that try to derive which of them are statistically important. First try to are statistically important and say that these are practically important. That's not the flow. First think of those variables which might be practically important and collect the data for them. After that, see which of these are statistically important. That is the typical flow. So, which means the statistical importance is a necessary condition for practical. So, somewhere I will say it is a practically important only if it is statistically important. But but every statistically important one need not be practically important, right? This is the flow that I have to remember. Something is practically important, a variable is practically important only if it is statistically important, but just being statistically important doesn't mean it is practically important also. That is the kind of necessary and sufficient condition we need to be comfortable with. And for any, okay, just try to understand the bathrooms. What is that we are saying? On an average, one single bathroom, if I am increasing the bathroom by 12,600, and if I am increasing one bathroom, the price of the flat will increase by $12,646. This is only on an average. Now, what is the minimum increase that can happen? So this is what we try to build in as 95% confidence interval of the same. Now this is what we could see, the lower 95% and upper 95%, which means this value could lie anywhere between 6,490 to 18,801, which is coming out as the value plus or minus 2 times the standard error. So it is as good as saying the value minus two times the standard error to the value plus 2 times the standard error. Actually speaking, it's not exactly 2, it's 1.96 to be precise. On an average I can take 2, but yeah, slightly here and there. 1.96 times the standard error. So probably we'll see the values more or less in a particular range between this and this. So you could traditionally see in that particular range the mean minus 1.96 or 2 times the standard error to the mean plus 2 times the standard error. Right, probably somewhere in the middle it's falling, so you can take either 2 times or 1.96, somewhere in the middle it comes out, but this is the range. So which means at a minimum, to a large extent, there could be 6,400 increase in the price, and it may even result into 18 to 19,000 increase in the price by increasing one bedroom. So that should be the practical way I should interpret. It's not that every apartment price will increase by 12,600 if the number of bathrooms is increased by one. That's not the case. I have to utilize this confidence interval to really come out with an assessment on the same. So we are taking both the signal as well as the noise of the predictor to come out with useful conclusions regarding our analysis. And wherever we are concluding that a predictor is insignificant, we have to rerun the model by removing it from the set of predictors and rerun it only with the remaining set. So these are some of the basic aspects from the regression that we need to be comfortable with, whether it is single or multiple kind of a regression. Of course, there are quite many other aspects that are there, but as an interesting part, as a first step in terms of understanding the regression process, we need to be comfortable with aspects up to here at least, right?